And good evening for a second time. It only seems like 5 minutes since I was last talking to you, and this time we're talking about the science of Santa. So the question I'm trying to answer effectively is Santa compatible with the laws of physics? Or a different way of wording it, how many laws of physics does Santa actually break? So we know that Santa is allegedly this portly, jolly fellow with a white beard and a penchant for wearing, well, I would say red suits. If you want to say green, that's your business. Let's say that the classic idea of Santa is to wear a red suit. So even if we say that that is rather questionable fashion sense, that of course doesn't mean he can't exist. What about the claims made regarding his rather incredible feats? So he allegedly visits all households on Christmas Eve to deliver presents to all qualifying children. Let's think about his naughty nice list in just a moment in terms of what that ratio might be. And the question is, can we reconcile that particular statement about visiting all households on Christmas Eve? Can we reconcile that with our understanding of science? And in particular, I'm going to make use of some of the talks that I've given over the past few years. So I've got about 30 or so talks. Here's about half of them, and I'm going to look at whether any science delivered in any of those talks can actually help us with understanding what Santa does and how he might do it. So let's take that particular statement one more time, because we're going to take that statement, Santa visits households on Christmas Eve to deliver presents to children, and we're going to unpick that and see which bits of that stand up and which bits fall down. So let's start with how many children he's actually visiting. So, how many children get Christmas presents? Well, the Earth's population is 8 billion, a quarter of them are children. Let's assume that 50% of those children are eligible for Christmas presents. Again, let's not get into an argument about the religion of the students or their parents. Let's just assume Santa is generous enough to deliver presents to up to 50% of all the children in the world. So about 1 billion children or so get Christmas presents. And again, for simplicity, I'm assuming that on the naughty nice list, let's just assume for the sake of argument, naughty is 0% and nice is 100%, just to make the numbers easier. Okay, and Santa visits all of these. So the question is, how does Santa get around? What's his mode of transport? Okay, we can ask the question, can reindeer fly? Well, we know that insects fly, we know that birds fly, we know that pterosaurs fly, even though you don't see many of them these days. And we know that some mammals can fly. So what about reindeer? Well, if reindeer can fly, they choose not to do so for a lot of their time, especially when we're watching them. So there's very little evidence for flying reindeer. But as a scientist, I have to admit that absence of evidence is not the same as evidence of absence. So I've never seen reindeer fly, and I guess you haven't either, but that does not mean that they can't. So that is something that science cannot give a definitive answer on. But how fast could Santa and his sleigh actually fly? If he wants to visit 1 billion children in one night, which is about 36 hours, if he takes advantage of the rotation of the Earth and visits the time zones in a suitable order, he's got about 36 hours to do his job. He would have to travel at something like 2,000 kilometers a second. But that's only a tiny fraction of the speed of light, 0.007 times the speed of light. If he's moving at less than 1% of the speed of light, Santa is in no danger whatsoever of defying that particular law of physics, that nothing can travel through space faster than the speed of light can travel through a vacuum, 300,000 kilometers per second or so. Now, yes, we know that space can actually expand faster than that. The universe is indeed expanding at the moment, and there are some galaxies receding from us at speeds considerably faster than the speed of light. The expansion of the universe can be greater than the speed of light, but no object can move through space faster than the speed of light. And that's covered in one of my talks called Fiat Lux, where I look at the nature of light and, in a demonstration, measure the speed of light and measure the wavelength of light. There still seems to be some microphones on if you'd like to mute those. So, if Santa moves quickly through the Earth's atmosphere, wouldn't you end up with roast reindeer? Wouldn't the sleigh burn up from the heat? Well, we know that meteors and asteroids moving quickly through the Earth's atmosphere heat up, because the air in front of either the meteor or the asteroid, or presumably the sleigh, would be compressed. Some people talk about objects moving quickly through the air getting hot because of friction. Well, it's not actually friction, it's because the air can't get out of the way when you're dealing with very high speeds. The air can't move out of the way fast enough and hence gets compressed and heats up. This idea of compression produces heat is something that is actually key to the ABC of stellar evolution. I talk about the three factors that determine how stars behave. The C of the ABC is compression produces heat. In other words, if you start with a large volume of hydrogen gas and compress it under gravity, that compression produces heat and eventually ignites the star. I'm not going to go in at this stage about what the A and the B are. But we know that compression produces heat. Even if you have a very aerodynamic sleigh, you still can't get around the problem that if you want to move fast through the Earth's atmosphere, things are going to get hot. Doesn't that mean you'll end up with a bright light in the sky? Wouldn't the sleigh be glowing white hot? Well, if you take any object, doesn't really matter what it is, at room temperature it doesn't produce any visible light of any consequence, but if you heat it up to a few thousand Kelvin, it would glow white hot. So why don't we see the sleigh, if it's moving across the world at very high speeds, why don't we see flashes of light all through Christmas Eve night? Hot objects radiate light, so surely the sleigh ought to be easily visible. Well, maybe it was, referring back to the previous talk. But thinking about Santa as being responsible for the Star of Bethlehem is pushing your luck a little bit. But maybe bright lights in the sky are indeed due to Santa, and maybe that's the origin of a different identification of bright lights in our night sky. Well, there's actually another way of dealing with this problem, because there is a certain type of matter that we know about that does not emit or reflect or absorb light, or indeed any other type of electromagnetic radiation. And we know what that is because most of the universe is made of this particular type of matter. It's dark matter. Ordinary matter, when you heat it up, will glow white hot. But if you have dark matter and heat it up, it does not emit any electromagnetic waves. And therefore, if Santa was made of dark matter, then he could move through the Earth's atmosphere quite happily and not end up white hot. And if the reindeer were the same, then they would not be glowing or producing roast reindeer either. So maybe that's a sensible explanation. It might also explain why the sleigh doesn't show up on radar, because radar will not be absorbed by the sleigh. If you've got an app that you think shows where Santa is according to radar, that app is a fake. Because if you can track something moving slowly across the world, then it can't possibly be Santa, because Santa's got to go a lot faster than that. So we've looked at children and we've looked at visiting. What about the households that he visits? How could Santa get down so many chimneys? If we want him to visit 1 billion children in one night, he would have to squeeze down 3,000 chimneys every second. And that, of course, assumes that the house actually has a chimney. If Santa, regardless of whether his suit is green or red, if Santa is a rather large, rotund fellow, how can he possibly fit down a small chimney? Well, actually, that's not impossible, because the size of Santa is determined by the size of all of its atoms. And an atom is mainly empty space. An atom is a nucleus plus electrons. If all you had to do was replace the electrons with muons, which are, if you like, a heavier type of electron. Muons, we know, are fundamental particles which can change into electrons, so why can't Santa change all his electrons into muons, in which case all his atoms would end up 200 times smaller? In which case Santa would be 200 times smaller. So instead of being a fair fraction of 2 meters tall, he would only be about a centimetre or so tall, and he would fit down a chimney no problem whatsoever. So that's the only thing that Santa would need to worry about, and that particular weird world of the very, very small is just the title I give to a talk that refers to how quantum mechanics works at the level of electrons, nuclei, atoms, molecules, etc. But if it works at that level, why shouldn't it work for Santa? Now, yes, I agree, that doesn't help if you haven't got a chimney. So what if you've got a house or an apartment which doesn't have a chimney? How could Santa get inside? Well, there's a number of different explanations. One explanation is we come back to quantum mechanics, and we know that an object can tunnel through a solid object. For instance, if you want to get inside a house from outside, rather than going down the chimney, rather than opening a door or opening a window, you can actually tunnel straight through a solid object. One solid object can pass through another solid object by a process called quantum mechanical tunneling. That can happen, we know it can happen, we've built instruments that rely on that particular quantum mechanical phenomena, so we know it actually occurs. And if it occurs, why can't Santa actually use that to his advantage? So it's an unlikely process, but maybe Santa has figured out a way of making it a little more probable. So we've looked at children, we've looked at visits, we've looked at households. He does all of this, allegedly, on Christmas Eve. So we can ask the question, how can he make so many deliveries all in one night? Even if he's travelling at relativistic speeds between each delivery, how can everything be done in 36 hours? And again, there's more than one explanation for this, but perhaps we come back to, yet again, quantum mechanics, which tells us particles can be in two places at one time. So why can't Santa be in two places at one time? Not only does this get around the problem of him delivering presents over 36 hours, because he can be in this house and that house and that house and that house all at the same time, it also gets around the previous problem I mentioned. How can he actually get inside a house? Well, if Santa can be in two places at once, he can be outside a house and inside the same house at the same time. That's allowed according to the rules of physics as laid down in quantum mechanics. So this idea of particles being in more than one place at a time, if it applies to a particle, if it applies to an atom, if it applies to a molecule, why can't it apply to Santa? If for some reason you don't like that and Santa can only be in one place at a time, despite the fact that quantum mechanics allows otherwise, if he can only be in one place at a time, then there needs to be an alternative way to make the deliveries. And that is Santa could be capable of actually manipulating space and time. If he has to deliver presents to lots of locations, why can't he simply distort space so that all those locations are closer together? We know that space is distorted by mass. The topic of the talk in this case, warping space and time, is talking about how large masses distort space and how they distort time. So we know it's physically possible. So maybe Santa is, by some means, capable of manipulating space and time in order to allow him to make the deliveries to 1 billion children in one night. So we've looked at children and visits and households on Christmas Eve. What about delivering the presents? Well, how could Santa carry all of these presents? Even if the present for each child is quite small, we're still talking about 1 billion children, so we're talking about 1 billion presents. How could the sleigh hold that many presents? Well, it's not quite the problem that you may believe, because again, we can come back to the distortions of space and time. It is possible to distort space such that an object is bigger on the inside than it is on the outside. We know that because, for instance, black holes, which we now know to be effectively a fact rather than just a hypothesis, black holes are the extreme part of that distortion, where space is so distorted, a black hole, if you work out the volume inside the event horizon, it's larger than the volume you would calculate by looking at the outside of the event horizon. So we know that is a possibility. It's just a question of not understanding exactly how Santa actually does that. But it doesn't break any laws of physics for an object to be bigger on the inside than it is on the outside. We've known that for a long time through Doctor Who's TARDIS, but we now realise that it's possible in fact. An alternative, if you don't like the idea of objects bigger on the inside than the outside, an alternative is maybe space is more than just the 3 dimensions we can see. We know that the 3 dimensions, forward, backward, left, right and up, down, are the 3 dimensions of space that we're familiar with. But many people believe that actually space comprises more than 3 dimensions. In some cases, many more than 3, perhaps 10, 11, 12, more. So maybe Santa has figured out a way of storing all of those presents in a different dimension, to tuck them out of the way, to make it nice and tidy. Again, I don't know how he would do that, but it doesn't disobey any laws of physics that we understand as of now. Okay, you might say, yes, perhaps that's possible, but surely any of the things I've said up till now, wouldn't they need a huge amount of energy in order to allow Santa to do these rather incredible things? Santa plus a sleigh plus 1 billion presents, if they're moving at relativistic speeds, wouldn't this need a huge amount of energy? And the answer is yes, it would. But maybe Santa does have a huge amount of energy available to him. For instance, his sleigh could be powered by a black hole. A black hole would be enough to power a starship, so surely it's enough to power a little sleigh and 1 billion presents. The black hole wouldn't need to be very big. A black hole smaller than an atom would produce enough energy to push the sleigh around at enormous velocities. It's enough to push a starship up to the speed of light. It's enough to push the sleigh up to very high velocities. There is another alternative. There's an energy source available to Santa that we've overlooked up to this point. It's the elephant in the room. It's the obvious thing. What happens to all the mince pies? Okay, different cultures around the world don't necessarily offer Santa a mince pie. It might be a cookie or something else, but there's usually a treat left for Santa. What happens to all of this? What if Santa could convert the mass of all the mince pies that he's left into energy? We know that E equals mc squared. So let's work out how much energy would be available if Santa somehow managed to extract the energy from a mince pie. A mince pie is about 50 grams or so. So if E equals mc squared, we put in 50 grams and the speed of light squared, and we get about 5 times 10 to the 15 joules out of every mince pie. How many mince pies does he get on Christmas Eve? Well, we don't know, but let's assume it's a few percent of all the households that he visits. So let's say it's of order, let's say 20 million mince pies. 20 million times the number I've just calculated gives us a total of 10 to the power 23 joules at his disposal. And it's difficult to work out how much that is because not many people work in joules, and 10 to the 23 is a really big number. So let me put that into terms that we can make some sense of. Imagine the energy output of a nuclear power station. Imagine the energy output added up every hour of the day, every day of the week, every week of the year, for 1 million years. The energy output of a nuclear power station running 24/7 for 1 million years. That total amount of energy is the amount of energy that you could get from the mince pies. So that's a huge amount of energy. How do you extract E equals mc squared from a mince pie? Yeah, okay, it's not altogether obvious. Santa must be able to do it somehow, otherwise how do you explain how he does what he does? Well, you could, in principle, take all of your mince pies, and you could take an anti-mince pie and collide them together in the Large Mince Pie Collider at CERN, and that would release a huge amount of energy. But that has the problem that the energy release would be wherever the collider is, and Santa really needs this energy somewhere else in the world. And of course the other problem is, where do you get all of the anti-mince pies from? So maybe that's not such a good idea. Is there an alternative way of extracting E equals mc squared from a mince pie? Well, it's difficult to get all of that energy out, but there is a very efficient way of extracting a large fraction of E equals mc squared from a given mass. You may think that stars are quite efficient. You start with a large ball of hydrogen and you end up burning or fusing that hydrogen into helium, and that gives you enough energy to keep the star burning for maybe tens of billions or even trillions of years. So that might sound like a very efficient process, but actually nuclear fusion is only barely 1% efficient. A much more efficient way of getting energy out of mass is to drop the mass into a black hole. So maybe Santa has already got one, because that was what was originally thought of perhaps as a power source for the sleigh. So if he does have a black hole to hand, if he drops the mince pies into a black hole, it will release energy. And we know that dropping matter into black holes is very efficient because, for instance, matter falling into a black hole can produce a quasar, an active galactic nucleus. A quasar produces a huge amount of energy because of the matter falling into it. Well, it's probably not mince pies. It's more likely to be hydrogen gas falling into a black hole at the center of a galaxy can produce huge amounts of energy because a large fraction of the matter is converted into energy. This is something I mentioned in a lockdown challenge that I undertook in 2020 when I tried to image a quasar that's on the other side of the observable universe. It's some 25 billion light years away. It's receding from us at about twice the speed of light, and yet it's possible to photograph it without using a telescope. I used a camera and a telephoto lens and caught the light from a quasar. Despite this fantastic distance, despite the fact that it's receding from us at fantastic speeds, greater than the speed of light, it is still possible to catch this light because so much energy is resulting from the matter falling into the black hole. So we know that is a possibility. As to how much energy you can get out of a mince pie falling into a black hole, well, I found it very difficult to find out. I tried Googling it, but I could not find anybody that's done any studies that tell us how much energy you can get from a mince pie falling into a black hole. It's as if nobody wants to know. Okay, an opening there for anybody that wants to do that research. Okay, maybe these are explanations, but how could actually that happen? They might be possible in the sense they're allowed by the laws of physics. But how, for instance, could Santa possibly manipulate space and time in the way that I've been describing? Well, perhaps you're looking at this from the wrong angle. The question is, why not? Who says Santa has to be human? Why can't Santa be more like Yoda? Who says Santa is somebody that looks vaguely Caucasian? How do we know Santa doesn't have green skin and big ears? Children are always told that you must go to bed before Santa visits, so nobody has actually seen the real Santa. So maybe that is what he looks like. There have been attempts to reconstruct Santa in the sense of reconstructing Saint Nick. If you believe that Santa and Saint Nick are the same person, Saint Nick was a Greek bishop in Turkey, and using his skull and facial reconstruction carried out by the Liverpool John Moores University, they've actually reconstructed what they think Saint Nick actually looked like, and of course embellished it with a white beard. So maybe that does or doesn't look quite like the popular indication of what we think Santa is looking like, again with the red suit because of the Coca-Cola input. But regardless, we don't actually know, therefore he could actually be green-skinned and big ears. So returning to the original question, how many laws of physics does Santa break according to his alleged feats? I would argue the total number of laws that he breaks is none, because everything he does has an explanation, perhaps a rather outlandish explanation, but it's an explanation that fits within the laws of physics. So feel free to draw your own conclusions about the existence or otherwise of the portly jolly fellow with a white beard and a penchant for wearing red suits. And regardless of your conclusion, I say to you for a second time, I wish you all a very Merry Christmas. Thank you for listening.